This is John Black, Super Chemist, and this is a video from a playlist called New and Updated Frames of Reference, and this particular video is about relativity. Now in part 1 we learned that a frame of reference is just a place where you get your point of view from. That's all it is. What does relative mean? It just means compared to. You got a standing still guy and your car moving 50 miles an hour to the right. Relative to the frame of the reference of the standing still guy, the car is moving to the right at 50 miles per hour. What am I saying? I'm just saying compared to this dude, this car is moving miles to the hour to the right. That's all I'm saying. Now you might say, well, we know this guy is standing still. He's going 0 miles an hour. He's the one that's standing still. But I want you to think about it. The earth is spinning. So if you're looking above the earth, this man would be moving. He isn't moving at 0 miles an hour. And the earth is orbiting around the sun. And the solar system is orbiting around the galaxy. And the galaxy is moving through the universe over 1 million miles an hour, or whatever it is. So standing still and moving at constant velocity are relative things. You can only compare it to something else. Because you can never really stand still. So everyone's moving. There is a standing still spot, but we don't know where that standing still spot is, so we can't compare things to it. So in our standing still frame, this guy right there, that we're standing with him, we see this guy running towards us at 50 miles an hour. We see this van going away from us at 50 miles per hour. That's relative to or compared to us. That's what's going on. But what about the frame of reference of the moving man? His place where he gets his viewpoint is moving. So from his viewpoint, what will he see this doing and this doing? He will see the van going 50 miles an hour this way. He will see this guy standing still, and he will see himself moving at 50 miles an hour. Because this is a stupid, scenario. That's what he is going to perceive. He's going to see the road. He's going to see trees, the grass, the rocks along the road, all the little buildings. He's going to know this man is standing still, this man is moving 50 miles an hour, and he knows that he's running. And so he knows he's going this way at 50 miles an hour. But I want you to think of this. What if this was a spaceship, this was a spaceship, this was a spaceship, and they're all out in outer space, all floating, all inertial, meaning they're floating, and the rest of the universe is gone. This is a thought experiment. When you do a thought experiment, when you do relativity, you have to go down to the bare variables. And all of the variables like the universe, you need to get rid of them. The trees in the background, the road, the planet, you got to get rid of all that background. Otherwise, you're being an idiot. You can obviously see everything. You're going to know what's going on. But if this guy's in a spaceship and he can't see any background, and this guy can't see any background, and he can't see any background, how can you tell who is moving and who isn't? There's only 3 things in the universe, these 3, and they're all floating. Everything in space is moving, so nothing is stationary. Think about it. Even the biggest star, the biggest thing you can think of, is still floating through space. And you're attached to it, or whatever is attached to it. Everything is moving. There's no such thing as standing still. Remember what we said in the last 2 videos. If you're moving at a constant velocity inside this car or spaceship, and everything else is moving at that same constant velocity, you cannot perceive that any movement in that direction that you're moving at. Because think about it. If you're going 50 miles an hour, and I have this lighter in front of your face, and it's going 50 miles an hour, that same direction, to left to right, it would just look like it was just stuck here. That's why constant velocity and standing still are the same, because no matter what your velocity is, you get the same physics results. But since you get the same physics results standing still or at constant velocity, we can interchange these. We can say they're the same, kinda. And we can pretend, if both are going at constant velocity, we can pretend one is standing still and one isn't. And that's what we would do in this situation. From this guy's point of view, his frame of reference, where he sees stuff, compared to him, relative to him, this shit would be moving 50 miles an hour this way, this one would move 50 miles an hour this way. But to this guy, he's going to be floating just as well as this guy. So who's to say who's standing still and who's constant velocity? Since you get the same physics results, you might as well say, and have this rule, say that you're standing still. So in his frame, he's going to pretend he's standing still. And if he's standing still, what would he see? He would see this guy going 100 miles an hour this way. He'd see this guy going 50 miles an hour towards him, because the rest of the universe isn't there. You can't tell everyone. They're all floating. So this guy is going to see this one coming 100 miles an hour that way, and this one going 50 miles an hour this way. Going back to this original thing here, why would we do this? Why would we say this man, from his frame of reference, the truck is moving 100 miles an hour this way and he's just standing still? It's easy math. Why would you? Let me ask you, would you rather do the math where this guy's going 50 miles an hour this way and this guy's going 50 miles an hour that way? Or would you rather do the math where you have this guy standing, we pretend that he's standing, and this guy's not going 50 but 100 miles an hour this way? That's easy math. This? No. That ain't easy math. That's harder math. Why would we do it? If it's the same exact physics results, it's the same math, you're going to get the same answer. Why do it the hard way when you could do it the easy way? But going back to the thought experiment where they're all spaceships, then you're forced to say someone is standing still. If you woke up with amnesia, you don't know what's going on, but you know you're floating, logically you would know that you're moving at constant velocity because nothing can stand still. If you're floating in space, what would stop you from moving? You would know logically that you are moving at constant velocity, but come on, we would all get up and look around and we'd say we're floating, we must be standing still. If we know we're at constant velocity, what velocity would we pick anyway? If we're going to have to pick anything, you might as well just put zero velocity. That's the easiest math. It's the easiest to conceptualize everything. Even though you know logically you're moving, you're going to obviously assign your coordinate system where you're standing still and everything else is moving. Because it's easy. When we said that this spaceship perceives this guy to be moving 100 miles an hour, that doesn't mean that he's moving 100 miles an hour. That just means he perceives it because relative to him, if he adds up both of these velocities, it's 100 miles an hour. But look at these three photons. They're going to the right here. And you got a spaceship. It's going to the right with that photon. This one's standing still, and this one is going towards the photon. Now, when you move away from the photon, it's stretched out and becomes red. It becomes less energy. Here it just stays the same because you're standing still. When you move towards it, the photon gets all bunched up and it has more energy. Now, does this mean that there's magic or some leprechauns came and took the energy away from here and leprechauns gave the energy here and the light just changed because of your perception? No, your perception doesn't change reality. That's insane. Okay, what happens is you added your energy. This doesn't get more energy. No, you're just adding up your energy going to the left and this photon's energy going to the right, and it adds up to more energy than if you were just standing there and the photon was coming towards you. And it'd be even less energy if the photon was coming this way and you were going away from it. Just like over here. If you were running at 49 miles an hour to the right and the car is going 50 miles an hour to the right and it hits you, it's going to feel like you got hit by a 1 mile an hour car. But does that mean that you changed the speed of this? It's still going 50 miles an hour. It's just you added up your velocity and the car's velocity. Here you added up your energy and the photon's energy. The photon didn't gain energy. The energy, you added the energy. You took the energy away up here. You added the energy here. The photon didn't change in any way, shape, or form. If I'm this guy and I have you stand here and I throw a rock at you, it's going to hurt. But if I throw a rock at you and you're running this way, and as soon as you hit this spot, I time it so you get hit by the rock in the face, it's going to hurt less. Just like over here. If I'm throwing it at 50 miles an hour and you're running 49 miles an hour this way, it's going to feel like a love tap. But what if you're running towards me at 50 miles an hour and I'm throwing rocks at you at 50 miles an hour? that's going to feel like double what this guy got. Now, did the ball change its mass? Get more mass, and it's it's hitting this one more and hitting this one? No. Did it change its energy? No. It didn't change its energy. You added your energy to the rock when you ran towards it, and when you ran away, you're taking energy away from the ball. It's not that the ball has a different velocity, or the car has a different velocity, or this has different energy. No. You're adding your energy to it by having your frame either move towards it or move away from it. If your frame moves it towards it, then the velocity that you get, it's not that the truck starts going 100 miles an hour. It's you're adding your velocity to its velocity, and 50 and 50 is 100. Just like up here. You are running away from the photon, so the energy that it gets when it hits you in the eye, just like a rock or a car, is going to be less. Here, when I hit you with the rock or the photon, you're running into it. So you get the energy of this and the energy of you. And the reason why it's blue and red here is because as it's going this way, you're moving into it. You're collecting this one, and then you collect this next trough and this next crest faster than you would in these two scenarios. You're bunching it up. It's called the Doppler effect. And here you're bunching it away. So relativity doesn't mean that there's magic and we're all living in different universes and you have different velocities and different energies and different masses, and depending on what frame you're in, because that frame is in another universe and leprechauns come out and did stuff. No. You, in a moving frame towards something, you add velocities or you add energies, or and when you move away, you take away the energy from whatever rock was thrown at you, or whatever car is coming at you, or whatever photon's coming at you. In the frame of reference of this guy, he sees blue light. Does that mean it is blue light? No, it's green light, man. It's just from his frame moving into it, it's blue. This guy, does he see red light? Yes, he perceives it. That's true. But did the light change? No. He just was running away from it. So from his frame of reference, the light is red. Is it right? Red? No, it's green. It's just he's moving away from it. Does this person actually see blue light? Yes. Because he's changing the frequency of the light by moving into it. He's collecting the troughs and the crest more often. So the frequency is green, but him moving into it, the light doesn't change the light. It changes the speed that he gets the information about the light. He's collecting the information a lot faster by moving into it. Here he's moving away from the light, so the information, he collects the trough and the crest and the trough and the crest, he collects them at a slower rate. And your photon collectors, your eyes, or your electronic photon collectors, they work by not color. Color is a made-up thing. It doesn't even exist. It's just in your brain, in your head. Your brain assigns a corresponding color to a corresponding energy. So here he gets less energy to his photon collectors, his eyes. And his eyes tell him that it's red. There is no such thing as red, though. It's just about energy. And this, he just gets less energy because he's going away from it. And it's collecting the troughs and crest at a slower rate. So that's less energy. So that's red. Your brain interprets it as red, and your brain interprets this as blue. But just because you interpret something, if I see a mirage because I'm going down a road and I see a mirage, that doesn't mean the mirage exists, okay? It just means I perceive it to exist. So it doesn't matter if you're talking about velocity, you're talking about momentum, you're talking about energy. The difference that makes it relative has nothing to do with magic or anything like that. Energy doesn't come from nowhere. It comes from you. It comes from you running 50 mile an hour, you running towards the rock, from you running towards the photons. Okay, it's not the energy doesn't come from. We don't know where it comes from. It comes from you. Same way with this in the pain. It's not that the ball got faster or got more mass or got more energy. You ran towards it.